So let's skip to the next one on the utility of virtual on-body acceleration data.
Hi everyone, my name is Zikang Leng, and I'm an undergrad from Georgia Tech. In this work, we proposed a metric to measure the subtlety of activities from videos, and we correlated this metric to how well virtual MU data will benefit the downstream classifier for these activities. So a long problem in the human activity recognition or HAR field is the lack of large label data due to the cost of annotations and issues with privacy. Recently, IMUTube was introduced to extract virtual MU data from videos, and the virtual MU data extracted has been shown to improve the downstream classifier performances. But IMUTube was only tested on activities with coarse movements such as gym activities or locomotion, while many daily activities such as driving, riding, or reading involves more subtle movements. Hence, we propose a motion subtlety index, or MSI for short, to measure the subtlety of activities from videos. So for a given video, we first perform optical flow estimation and 2D pose estimation, where the 2D pose estimation tells us the location of the sensor joint that's our interest. In this case, it's the wrist joint, while the optical flow estimation tells us the amount of local pixel movement around the sensor. Afterwards, we averaged the normalized optical flow around the sensor location, and we take the standard deviation of these averages. Lastly, we take the negative exponential of the standard deviation to obtain MSI. We note that computing MSI is 10 times faster than extracting virtual MU data for the same video. So to validate IMUTube on fine-grained activities, we decided to use the head AW dataset with 17 daily activities, and we calculated the MSI for each activities. The virtual MU data in this case was extracted from Kinetics 400, a large-scale video dataset. In this case, we first start with a classifier that's trained only on real MU data. Then we have a MSI threshold for which we will add the virtual MU data for activities that have an MSI lower than the MSI threshold. So on the x-axis here, you see the MSI threshold, and on the y-axis here, you see the absolute F1 score difference between the classifier that's trained on only real MU data and the classifier that's trained on both real and virtual MU data. As you can see, there's a negative correlation between the two, showing that activities with more subtle movements does not benefit from virtual MU data, and we see that the zero crossing point is at MSI equals 0.89. This shows that activities with MSI greater or equal to 0.9 are too subtle for IMUTube to capture, as they have very subtle motion characteristics that's limited by the current computer vision methods. So following this idea, we decided to test the concept of eating detection, which had an MSI of 0.86, which is lower than the threshold of 0.9. So from this, we would expect that the virtual MU data would benefit the downstream classifier. So the result is shown on the left. And as you can see, the classifier trained both on real and virtual MU data does significantly outperform the classifier that's trained on real MU data, validating our hypothesis that eating, which has an MSI of 0.86, does in fact benefit from virtual MU data. So to recap what we did in this work, we introduced MSI, a metric for measuring the subtlety of activities from videos, and it is 10 times faster than extracting virtual MU data, and we correlated this metric to how well virtual MU data will benefit the downstream classifier. Since it is 10 times faster than virtual MU data extraction, we believe it will be useful for predicting the usefulness of virtual MU data even before the virtual MU data is extracted to potentially save time and resources. Thank you. That's all for my talk, and I'll take any questions now.
I commend you on a very succinct summary of what your paper was about. Thank you. My question is, were you focused mainly on activities that use the arms and the hands? Did you look at other body parts?
In this study, yes, we mostly were focused on the wrist, since that's where mostly where smartwatches are deployed. But the same idea could be applied to activities. Let's more focusing on the other body part, like maybe like walking or running and etc. Because we can still measure the subtlety of those activities using the same method. Just like we're focusing on a different location.
Right, let's thank the speaker again.